once again. This we have just defined effective stress, effective concept we have explained, and how to calculate effective stress because of the self weight of the soil, just we have seen. And now this we have seen that permeability seepage, and we have seen effective stress. And during permeability and seepage, we have shown that because of this porous in nature of soil, and there is, if there is a change in head, say upstream and downstream, then water will flow from higher head to lower head. So, that means there can be in the field there can be a number of situation that soil water in a static condition, that is a fixed groundwater level, and there is a fixed ground surface, and for that we can find out what is the effective stress at a depth. Now, the situation may change, water table may rise, that is one situation, and then sometime there is another situation that water may flow through the soil, and again flow can be in the different direction, flow through the soil the upward direction, that means from the bottom to up, and also there can be flow of water from the top surface to the bottom, another situation, and there may be no flow. So, there are different situations can arise in the field, and because of that how effective stress will change, that we will examine one by one, and we will see the application also simultaneously. And sometime that in a static condition it is a quite stable, but when there is a flow take place either downward or bottom downward or upward, and sometime we will see that sometime flow may cause the danger. Different ways danger, one is actually I have shown already, but once again we will show here, that is critical hydraulic gradient, how critical hydraulic gradient play a role to make the condition bad, that will show one by one. And also because of the flow from when it is up from the up to downward side, then sometime we have seen that some seepage pressure will act. So, that actually what is the quantity, and that we will see one by one. So, particularly I will start with no flow conditions. So, suppose this is a situation here, and you can see that there is this is a soil mass, this is a soil mass, and it is a through this soil, and water head is applied here, and from the bottom also it is connected to another tank, and the water is continuous through this end to this end, A to B. So, but since there is a overflow from both places, if there is a water more either here or here, it overflow will take place and maintain same level. So, if this is the level maintained, then this will be in a very much in equilibrium condition, and there is no flow of water through the soil. So, this condition already I have explained, but this is a case separately, since we are taking I have taken as 3 cases, I will show one by one. This is one of them, that is no flow condition, and at this case you can say above the soil we have head suppose Z2, and soil thickness or height is Z1. And so, under this if I consider since there is a no change in head, there is no change of head loss, there is no head loss. So, there is no flow. So, everywhere if you go, it should be same hydrostatic pressure you can get. So, because of that, within the soil mass at a point Z, suppose at a depth Z, from here to a Z depth we have considered a point. So, if I consider that point, then what would be U Z at that point? That means, what is the hydrostatic pressure at this point? As we know that hydrostatic pressure is nothing but unit weight of water multiplied by depth Z. So, what is the total depth at this point? This will be Z 2 plus Z. So, this is the total head at this point if I consider. So, this is the total water head. So, at this point because of this water, what is the pressure? So, that is what U Z is Z plus Z 2, Z plus Z 2 into gamma W is the U Z. And at any depth Z, what is the total stress? So, that means I want to find out at this level what is the total, that means sigma, that is total stress. I have got U, next I am getting total stress. Suppose this is like this, what is the stress here? What is the stress here? Total stress. So, to find out this total stress, what you have to do? We have to consider whatever there above this line, I have to take weight of that and divide by area. And since I can assume that I can assume that I have considering this over a unit cross section area. So, if I can find out the weight itself will be the pressure. So, to find out this, I can first find out the weight of this and then I find out the weight of this soil. So, this is the way I have done. So, Z plus Z 2 water weight is already there, and this portion is taken Z into gamma submerged. The additionally up to water height was there, additionally you have take submerged unit or buoyant unit of water soil, and this is the way we have taken. I could have taken other way also, I could have taken this one also like this, Z into gamma saturated. If I take this one, and in that case I could have taken here Z 2 into gamma W. I could have taken this way also, but ultimately so this one actually I can do gamma sat, and the gamma sat is nothing but so gamma submerged minus gamma W. So, these if I do and these are actually similar, and so at this point I will calculate either this way. If I take saturated unit weight total I take, then only Z I will take, and when I will take this way, then I will take only water height, only Z 2 is acting there, only this can be taken. So, either this way or this way, gamma submerged into Z, in that case water only Z 2 into gamma W, and when I will take Z into gamma saturated, that means gamma saturated I am taking means I am taking water weight also in this. So, because of that I will not take separately water weight. So, this will be if you do that, you can see gamma submerged in plus gamma W, gamma submerged in plus gamma W is the gamma saturated. Okay. So, because of that you can see if I take Z into gamma W, Z into gamma W. So, here if you multiply, so Z gamma sub plus gamma W, gamma sub plus gamma is gamma sat. So, this is coming. So, that means if I take Z into gamma sat here from this portion saturated depth of the soil, that means water is already included. Because of that I am not considering water separately here, only water depth Z 2 into gamma W I have taken. So, it can be done either this way or it can be done this way. If I do this, gamma submerged will be used, if I use this, gamma saturated will be used. Now, once you do this, this is total sigma at Z, at depth Z, and this is U at Z, then gamma effective stress by definition we know that sigma Z at any depth minus U Z, and sigma Z minus U Z, if I now put sigma Z actually is Z into gamma submerged, this I have taken, Z plus Z 2 into gamma W, this I have taken this, minus u z plus z2 into gamma w, and you can see z plus z2 gamma w, z plus z2 gamma w here this will get cancelled, ultimately z plus gamma submerged. So, that means when there is no flow and then at any depth, if I want to find out what is the effective stress, then it is nothing but z into gamma submerged. You can see this, that the same thing whatever way I have shown there, you can see gamma w see total stress we have calculated. So, it is up to this z 2 into gamma w has come here, and z 2 plus z gamma w plus z submerged. So, this portion up to this is nothing but this, and this portion. So, at a depth z, and at this depth it will be z 1 plus z 2 gamma w, that means both plus z 1 gamma submerged. And when is water pressure you are calculating, you are getting C, it will be linear, and at this depth z 2 gamma w, at this z 1 plus z gamma w, and at this z 1 plus z 2 gamma w. And now, if I subtract from this to this, you can see it gets 0. And now, this minus this if you do, it z into gamma submerged, that whatever we have shown here. And if I take at this point, again it will be z 1 into gamma submerged. So, this is the depth. So, that means z into gamma submerged. Now, as I have concluded in the previous slide, that if the water table change any height above above the soil ground surface, this is ground surface. If water table goes here also, suppose if goes here also, again similarly up to that diagram will start from here, here also diagram will start from here and will get cancelled and start effective stress from here. So, there will not be any change, whereas if water table from here, if it goes down here, there will be change, that I will show later on. So, that means, so no flow condition, if I want to find out effective stress and it is fully saturated, suppose there is a ground and it is saturated here, and I want to find out what is the effective stress here. Then the gamma, if I know the gamma saturated here, then gamma saturated minus gamma w, that become gamma sub, and into this depth I will consider, that is z, that become sigma dash directly. So, one can do two ways, one can do first gamma saturated, this is the way directly I can do, or I can do gamma saturated into depth, I can do total, and u into gamma w is the pore pressure, and difference of these two become effective stress. That is that way also one can find out. So, this is actually no flow condition, that is static case. In fact, whatever I have discussed in the previous lecture, that almost similar, only thing I have shown that if I lift this one, if this tank is elevated slightly this side, suppose if the tank is taken somewhere here, tank height is raised here and this overflow is kept here, that means head is here, at this point hydrostatic pressure is more, at this pressure hydrostatic is less. So, because of this head change, the whole flow will take place in this direction. And again, if I take the tank somewhere here, tank I lower and bring it somewhere here, and overflow takes place from here, in that case water, if I apply here, because of this change in head, water will move in this direction. When water is moved in this direction, water moves in this direction, there is two different situation, and lot of changes will be there within the soil mass, particularly the effective stress, that we will see in the subsequent slides. So, you can see that this is the one, as I have mentioned there, that I have considered a tank is at lower height, and we are supplying flow here at a particular height, and the difference is h. So, because of this change in head at this side, then obviously flow will take place in this direction. and if this flow takes place this way, then what is the changes, what are the changes in effective stress, that we will see. And under this condition, I can draw the effective total stress, I can draw the pore water pressure, and then total minus pore water pressure, that gives you effective stress, and from there you can draw some conclusion. You can see here at this point, if I consider from, because of this head we are getting some head, but if I consider from this side, then I will get different water head. So, there is a change. So, if I consider u b here, so z 1 plus z 2 minus h. So, z 1 plus z 2 is the total height, minus h is the head at this, and whereas u a at that means, if I consider at from here at a, then you will get z 1 plus z 2 into gamma w. So, this it cannot have different, at equilibrium from both sides it has to be equal. How it will become equal? Because of during the flow there will be loss of head, and finally, it will become from both sides it should be equal. That means, you have to consider equal here only. So, that will be equal to z 1 plus z 2 gamma w. And so, if I want to find out sigma a at this point from considering this side, then you can see z 1 plus z 2 gamma w is there, z 1 over the entire depth, z 1 plus z 2 gamma w. So, z 1 plus z 2 gamma w is there, water head up to this acting. So, that will be there at total stress at this point I am calculating. And what is the additional? Because of the soil, since soil is underwater, it is a submerged condition. So, z 1 into gamma submerged. So, that I can consider. Otherwise, I can take any depth, I can vary it. So, at this point I get this total stress equal to z 1 plus z 2 gamma w or z 1 gamma submerged. So, I am getting stress considering from this side. Now, if I take sigma dash, sigma a dash, the sigma a minus u a, and sigma a will be z 1 plus z 2 gamma w plus z 1 gamma submerged, already just in the previous slide we have seen, and u, effective u is what? Whatever I am seeing from the other one. So, z 1 plus z 2 minus a, that means that is it is here and tank is here. So, this is h. So, at this point head is nothing but whatever z 1 plus z 2 was that, this is z 1 plus z 2, but actual head acting here, actual head acting here z 1 plus z 2 minus this h. That means, because of this flow the head h is lost. So, you have to find out this value. So, actual at sigma a, sigma a is calculated because z 1 and z 2 are there, gamma w, and soil was that into z 1. So, z 1 into submerged, this is total stress, and at this point because of this, what is the hydrostatic pressure giving? So, z 1 plus z 2 minus h, and this into gamma w. So, these two, actually difference of these two will give you at that point at a bottom at this point effective stress. So, this will be, if you see this z 1 plus z 2 gamma w minus z 1 plus z 2 gamma w. So, this is actually minus z 1 plus z 2 gamma w plus h gamma w. So, these and these will get cancelled. So, you will have z 1 submerged plus z 1 gamma submerged, z 1 gamma submerged plus h gamma w. So, this is that. So, that means, whatever I have seen, we have seen in the previous one that the only when there is a no change in head from the two sides, then only we have got Z 1 into gamma submerged. Now, when the flow is taking place from the soil downward direction, we are getting effective stress additional term, that is H gamma W. The H is the head loss which causing the flow. Because of this head loss flow is taking place. So, additionally that means this much H into gamma W is coming. Now, this can be very much generalized, that if I consider sigma z at any depth, sigma a dash. So, that z is actually, I can go back to the previous slide, I will go up to this after this. So, it is linear. So, that is what it is proportionate, sigma z dash, it will be z by z 1, sigma a dash z by z 1. So, that was actually, it was here like this, diagram was like this. So, this depth is z 1 and this depth is z, and at this z depth actually sigma a dash, this one is sigma z dash. So, if I proportionately sigma z dash, if I find out the sigma a dash z by z 1, it will be the this from the equal symmetric triangular symmetry of triangle. So, we can write sigma z dash, sigma a we have got, and this is the diagram, and sigma z dash we can get sigma a dash z by z 1, and if I do that. So, sigma a dash is this and multiplied by z by z 1, and you can see z 1 get cancelled. So, it will be gamma z into sorry. So, z 1 gets cancelled, z into gamma submerged, z into gamma submerged. So, z into gamma submerged is here, and you can see here it will be 8 z, it will be 8 z gamma w by z 1. So, this is coming h into z by z 1, h into z by z 1 gamma w. So, this term is coming. So, at any depth, that means this is the effective stress. Now, this can be further simplified, this is z into gamma submerged already we know, and h by z 1, h by z 1, that means head loss because of the flow through how much depth. Your sample was this much, this is z 1, and through this flow is taking place, and because of this flow through this head loss is h. So, as per our definition of hydraulic gradient, actually head loss over how much depth z 1. So, that means h by z 1, h by z 1 I can define as I, h by z 1 I can define as I. So, it will become, so ultimately z gamma submerged I z gamma w. So, that means what is the additional stress coming when flow is taking place from downward direction? That means whatever pressure already there in the static condition plus hydraulic gradient times z times gamma w. So, that is I additional, you have to I z gamma w to be added to the actual static effective stress in the static condition. This must to be added to get the effective stress in the flowing condition when flow is taking place from upward direction to downward direction. So, this is one case, that means additionally first case no condition, no flow, that means it was z into gamma submerged, and when there is a flow is taking place, it will be additionally I into z into gamma w to be added to get the effective. That means effective stress is increasing because of the flow taking place from upward direction to downward direction. Now, there is a third case we will consider, that is actually as I have shown before, that your the third condition whatever I have shown, that when this tank is elevated or lifted by some height, and you can see here, and this is the level here and this is the level here. Now, if I continuously supply water here, and then because of this the water is continuous throughout this, then water will try to flow through the soil in the upward direction. Previous case whatever we have taken, flow was taking place in downward direction, now flow is taking place in upward direction. If it goes upward direction, then what will happen, that to be seen. Again here actually if I consider from this side, you will get head actually equal to Z 1 plus Z 2 plus H, but if I consider from this side actually your it is Z 1 plus Z 2 only, Z 1 plus Z 2 gamma W. So, this way, but at this point because of this extra head it will flow will take place, but in equilibrium condition you will consider this is the head. So, this is the head we are putting, and finally, at this point head will become equal. So, because of the loss H. So, now at this point will be head will be Z 1 plus Z 2 plus H, that is the head which caused the flow actually, and sigma A at this point, that what is the total stress, it will be Z 1 plus Z 2 gamma W, and that means the gamma W is there from here to here already. So, that is there, plus because of soil weight it is Z 1 gamma submerged, this is done for all cases. So, it is done. So, sigma A is this and U A is this. Now, sigma A dash again sigma A minus U A. Okay. So, if I do this, then you can see Z 1 plus Z 2 gamma W plus Z 1 gamma submerged minus Z 1 plus Z 2 H gamma W. So, this is becoming Z 1 gamma submerged minus H gamma W. So, you can see now when flow was taking place from upward to downward direction, we have got one extra term compared to the static one, that was H gamma W, which was plus. Now, when flow is taking place from bottom to upward, then it is also giving an additional term which is equal to H gamma W. That means, when flow takes place from bottom to upward direction, then that means effective stress is decreasing, and this decrease again how much, that can be generalized with respect to hydraulic gradient. So, if I take next slide, you can see that sigma Z dash again same way, if I do your this was Z 1 and this was sigma A dash, and this is Z and this is sigma Z dash. So, proportionately if I do, then it will be again if I similar way if I do and simplify, you will get Z gamma submerged minus I Z gamma W. That means, when flow is in downward direction, then it will be Z into gamma submerged minus I Z gamma W, and when flow is in the upward direction, it is Z gamma submerged minus I into Z. So, that was plus, and now my I Z into gamma W. So, it is everything similar, only when you have to remember that when flow is in the downward direction, it will be adding, and when flow is in upward direction, it is decreasing. So, minus. So, now this decrease can actually can be sometimes so much that effective stress becomes 0, it can happen so. So, in that case, when this effective stress become 0, that time we can say I equal to I c, and that actually if I come from that definition, critical hydraulic gradient I c equal to I, and then you can see this if I equate to 0, then I c become gamma submerged by gamma W, and gamma submerged by gamma W, you know, the G s minus 1 by 1 plus E. Already we have defined or derived before, once again we are getting from this, that is gamma submerged by that time. Actually what we have done, we have considered equilibrium, that means force from downward direction in the force in downward direction, force in upward direction and equated, and from there we have got the critical hydraulic gradient as per definition. And again once again here considering the flow condition, whether it is upward direction and downward direction, and as I have mentioned, when flow is in downward direction, it is adding some extra stress or effective stress. When flow is in upward direction, it is decreasing the effective stress, and this decrease can be so much that effective stress become 0, and that condition, the condition called critical condition, and that is called the corresponding to that whatever hydraulic gradient you get, that is called critical hydraulic gradient. So, the critical hydraulic gradient, if you know the soil parameter like G and void ratio, then I can find out the amount of critical hydraulic gradient, and if your hydraulic gradient is more than that, then actually soil will collapse, that is the thing. So, what is the significance? So, whatever we have got here now, these are theoretical. Now, what is the significance of this? Significance is this, that when there is a flow takes place from downward up to downward direction, then that extra stress to be calculated, that the extra pressure will come to the foundation, that to be considered. And when there is a flow is taking place in the upward direction, that time the stress will be reduced, and it can be reduced so much that soil may not have an effective stress, and soil do not have effective stress, it means that it is like a fluid. So, because of that, there is when the hydraulic gradient become critical, at that point generally that called the situation is called quicksand condition. Quicksand condition, that means many times in some places people were standing and suddenly they sink inside the mud that is sand. That is what actually there may be a sand layer here, and because of some reason there may be some source of water coming from here, and it is causing the flow in that upward direction like this. And if it happens, if the flow happens like this, and if the head is so much that here effective stress is 0, then if you stand here, then you will not be able to stand there. You will just, because the soil does not have any strength, so you will sink inside, and that is a very dangerous situation. Many times it happens in the seashore and many places people sink. And to get escape from this, immediately when you feel that your feet is going downward, immediately you can flat your body. Flattening the body, what it helps? Because it will help the way, because you are distributing the stress, your entire body weight is coming through the feet, whatever stress giving at this point, and if you entire body, if you flatten over the soil, then intensity of stress is reducing. That way actually sometime quickly you reduce the stress and come to the you can escape from the danger. So, this is a quicksand condition. The significance of this critical hydraulic gradient is that if your head is so much, or which because of that its hydraulic gradient exceeds the critical hydraulic gradient, and if the hydraulic gradient exceeds the critical hydraulic gradient, then your soil strength almost come to 0, and when there is a 0 strength, then anything you put on it, it will sink simply. So, I think with this I will stop this one, maybe I will go next slide and do something next. Thank you.